The city library will be increasing the number of books it has at a rate of 5.4% per year. The library currently has 40,000 books. The equation 40,000 times 1.054 models the situation. All right, so we're going to be working with exponential expressions today, exponential functions to solve word problems, and we're going to mostly give you the word problems. But we want you to understand how these word problems and their equations work. So notice this 40,000. That's the 40,000 books that the library has at the beginning of the problem. That's what we call an initial amount. So the initial amount is the 40,000 books. In an exponential function, that's the a value, initial amount. Then we're asked, what is the rate of increase? Well, this is going up by 5.4% per year. There's two different things here. One of them is called a rate of increase, and the other is called the growth factor. Okay, well, the rate of increase is that interest rate. So that's 0.054. That's 5.4% per year. But the growth factor is this whole number in here, the 1.054. So you might be wondering, where's the 1 coming from? Well, think about this. If the library is increasing the number of books that it has, it keeps all the books it already has and adds more. So it has 100% of the books it currently has, plus an additional 5.4%. So that's a total of 1.054, or 105.4%. So the rate of increase is the amount it's changing by. The growth factor is the number we put in the problem so that we're not just calculating how many books it's going up by, but how many books it will have once it increases by that much. Now we're asked to actually answer a question about this scenario. How many books will there be in 12 years? Well, X stands for the number of years. So Y, the total number of books in the library, will be 40,000 times 1.054 to the power of 12. And I need to make sure that I use my order of operations when I do a problem like this. So when I go to my calculator, the first thing I'm going to do is the 1.054 to the power of 12. And that's a really crazy number. It looks like it's around like 1.879. Like that's a really, it's being multiplied by itself again and again and again. So it's a really long decimal. I don't want to have to type that in again. So now that I've got that decimal, I'm just going to hit times 40,000. And that will be my answer. It's over 75,000 books. Now, notice my calculator is giving me an enormous number of decimals. It's really of no meaning to us at all because we're talking about a number of books. So in this case, it actually probably makes sense to round off to the nearest whole book. So 75,187.79, that's going to round up. So I would say that I have 75,188 books. So approximately equal to 75,188 books, because the library is not going to have a part of a book. Let's look at the next problem. A fisheries manager determines that there are approximately 3,000 bass in a lake. The population is decreasing at 2.3% each year. So the bass population is not doing very well in this lake. There's actually fewer bass from year to year remaining in the lake. The equation 3,000 times 0.97 to the x models the situation. We're first asked to look at the pieces of this problem. So the initial amount is the 3,000 bass that are in the lake when the model is formed. Now the rate of decrease, we're going down at 2.3% per year. As a decimal, that's 0.023. And then we're asked, what's the decay factor? Now notice before we were asked for a growth factor. This time we're asked for a decay factor. So a growth factor happens when we're increasing, but a decay factor happens when we are decreasing. Now remember, in the growth problem, it was like 100% plus 5.4%. So that was 105.4%. Well, this time we're decreasing, so we're not going to add, we're going to subtract. If we have 100% minus 2.3%, we think about how we do that. Well, we do a lot of borrowing, right? This would be a 7. That would be a 7. That would be a 9. That's where that 97 comes from in the problem. In fact, it really should be 0.977. That would be a little bit more accurate in this case. But we'll use the number that they gave us when we do the calculation. But really, 0.977 should be the decay factor. Actually, let's change it. I think that's really just a typo. Throw that extra 7 in there. Because when we do the subtraction, that's how that turns out. Because 10 minus 3 is 7, and then 9 minus 2 is 7. And then that would just be a 9. So we're asked how many bass will live in the lake after 4 years. Well, X is the number of years, and Y is the total number of bass in the lake. So we have Y equals 3,000 times 0.977 to the power of 4. And just like we did in the last problem, we're going to make sure to follow the order of operations. So first, we're going to do 0.977 to the 4th. Which gives us this crazy decimal. And then we're not going to retype it. We're just going to hit times 3,000. Oops, I just did 30,000. Let me take that back one. Again, we're not looking for parts of fish. That's kind of gross. We're looking for whole fish. So 2,733.3 is going to round down. So there are approximately 2,733 bass in the lake. Suppose 30 flower beetles are left undisturbed in a warehouse bin. The beetle population doubles each week. So the function f of x equals 30 times 2 to the x gives the population after x weeks. All right, we're asked what's the initial amount? Well, there were 30 flower beetles in there. The growth factor is 2 because that's the b value if we're thinking of this as y equals a b to the x. Now, if I wanted to ask what's the rate of increase, well, it's doubling, so there's twice as much. It's like 200%. What will the population be after 56 days? Now, wait a minute. This said X weeks, and now they're giving me days. We need to pay attention to that. If I'm given days, I need to divide by the fact that there's 7 days in 1 week to get the number of weeks. So I shouldn't be plugging in 56, I should be plugging in 8. So I've got f of 8 is equal to 30 times 2 to the 8th. And just as we've done before, the power needs to come first. So first we're going to do 2 to the 8th. Whoops. 2, oh goodness. Clear. 2 to the 8th. There we go. 256. So this is 30 times 256. So 7,680 beetles.